Welcome everyone. It is 3 p.m. and it's time for the Server Room Show. This is episode 77. Today I will continue what we started in episode 76, talking about three non-Unix operating systems, three very strange operating systems, which are not what you might be used to, even though they build some of them. For example, Plan9 we're gonna talk about today builds on the Unix concepts, and it was made in Bell Labs where Unix was born before. But Oberon we talked about in episode 76 is completely a different breed, and today I will talk about Plan9, and if I have time I will also talk about Inferno. If not, I have to put that for a different for the next episode. So episode 77, let's scroll and continue with Plan9. I know many of you, at least in the Anon Radio sphere or social group, or however you want to call it, I know many of you know Plan9, many of you love Plan9. Personally, I look at Plan9 and I don't even know where to start with it. I did try to reach out by an email to Ori Bernstein, whose YouTube video I even added in the show notes, because he have a quite a long talk, like nearly an hour and a half, an hour 20-minute talk back in 2019 about Plan9, and he shows many things of the operating system, but he never replied to me. So you will have to be happy with me talking about Plan9. Plan9 has that great bunny mascot called Glenda. You can see a drawing of Glenda in the show notes, and also some screenshots of Plan9. Plan9 from Bell Labs is a distributed operating system originating in the Computing Science Research Center, CSRC, at Bell Labs in the mid-80s, and building on Unix concepts first developed there in the late 1960s. The final official release was in early 2015. Under Plan9, Unix is everything is a file metaphor is extended via a pervasive network-centric file system, and cursor addressed terminal-based I/O at the heart of UNIX-like operating systems is replaced by a windowing system and graphical user interface without cursor addressing, although RC, the Plan9 shell, is text-based. The name Plan9 from Bell Labs is a reference to the Ed Wood 1959 cult science fiction Z movie Plan9 from Outer Space. The name of the project's mascot, Glenda, the Plan9 bunny, is presumably a reference to Wood's film Glenn or Glenda. The system continues to be used and developed by operating system researchers and hobbyists. Plan9 from Bell Labs was originally developed starting in the late 80s by members of the Computing Science Research Center at Bell Labs, the same group that originally developed Unix and the C programming language. The Plan9 team was initially led by Rob Pike, Ken Thompson, Dave Presotto, and Phil Winterbottom, with support from Dennis Ritchie as head of the Computing Techniques Research Department. Over the years, many notable developers have contributed to the project, including Brian Kennigan, Tom Duff, Doug McElroy, Björn Stustrup, and Bruce Ellis. Plan9 replaced Unix as Bell Labs' primary platform for operating system research. It explored several changes to the original Unix model that facilitate the use and programming of the system, notably in distributed multi-user environments. After several years of development and internal use, Bell Labs shipped the operating system to universities in 1992. 3 years later, Plan9 was made available for commercial parties by AT&T via the book publisher Harcourt Brace, with the source licenses costing $350. AT&T targeted the embedded systems market rather than the computer market at large. Ritchie commented that the developers did not expect to do much displacement given how established other operating systems had become. By early 1996, the Plan9 project had been put on the back burner by AT&T in favor of Inferno, intended to be a rival to Sun Microsystems' Java platform. In the late 1990s, Bell Labs' new owner, Lucent Technologies, dropped commercial support for the project, and in 2000, the third release was distributed under an open source license. A fourth release under a new free software license occurred in 2002. A user and development community, including current and former Bell personnel, produced minor daily releases in the form of ISO images. Bell Labs hosted the development. The development source tree is accessible over the 9P and HTTP protocols and is used to update existing installations. In addition to the official components of the OS included in the ISOs, Bell Labs also hosts a repository of externally developed applications and tools. As Bell Labs has moved on to later projects in recent years, development of the official Plan9 system had stopped. On the 23rd of March 2021, development resumed following the transfer of copyright from Bell Labs to the Plan9 Foundation. Unofficial development for the system also continues on the 9 front fork, where active contributors provide monthly builds and new functionality. So far, the 9 front fork has provided the system Wi-Fi drivers, audio drivers, USB support, and built-in game emulator, along with other features. Other recent Plan9 inspired operating systems include Harvey OS and Yehan OS. In 1992, Plan9's first edition, released by Bell Labs to universities. In 1995, Plan9 second edition, released by Bell Labs for non-commercial purposes. In year 2000, Plan9 third edition, released by Lucent Technologies under an open source license, and later in 2002, Plan9 fourth edition, again released by Lucent Technologies under a new free software license. The design concepts regarding Plan9, as we said, Plan9 is a distributed operating system designed to make a network of heterogeneous and geographically separated computers function as a single system. In a typical Plan9 installation, users work at terminals running the Windows system called Rio, and they access CPU servers which handle computation-intensive processes. Permanent data storage is provided by additional network hosts, acting as file servers and archival storage. Its designers state that the foundations of the system are built on two ideas: a per-processor namespace and a simple message-oriented file system protocol. And this statement is from Rob Pike. The first idea, a per-process namespace, means that unlike on most operating systems, processes running programs, if you want to call them like that, each have their own view of the namespace corresponding to what other operating systems call the file system. A single path name may refer to different resources for different processes. The potential complexity of this setup is controlled by a set of conventional locations for common resources. The second idea, a message-oriented file system, means that processes can offer their services to other processes by providing virtual files that appear in the other processes namespace. The client processes input-output on such a file becomes inter-process communication between the two processes. This way, Plan9 generalizes the Unix notion of the file system as the central point of access to computing resources. It carries over Unix's idea of device files to provide access to peripheral devices like mice, removable media, and so on, and the possibility to mount file systems residing on physically distinct file systems into a hierarchical namespace, but adds the possibility to mount a connection to a server program that speaks a standardized protocol and treat its services as part of the namespace. For example, the original Windows system called 8.5 exploited these possibilities as follows. Plan9 represents the user interface on a terminal by means of three pseudo files. Mouse, which can be read by a program to get a notification of mouse movements and button clicks. Cons, which can be used to perform textual input, output, and bit BLT writing to which enacts graphics operations. The Windows system multiplexes these devices. When creating a new window to run some programming, it first sets up a new namespace in which mouse, cons, and bit BLT are connected to itself, hiding the actual device files to which it itself has access. The Windows system thus receives all input and output commands from the program and handles these appropriately by sending output to the actual screen device and giving the currently focused program the keyboard and mouse input. The program does not need to know if it's communicating directly with the operating system's device drivers or with the Windows system. It only has to assume that its namespace is set up so that these special files provide the kind of input and accept the kind of messages that it expects. Plan9's distributed operation relies on the pair process namespaces as well, allowing client and server processes to communicate across machines in the way just outlined. For example, the CPU command starts a remote session on a computation server. The command exports part of its local namespace, including the user's terminal's device, mouse, cons, bit BLT, to the server so that remote programs can perform input-output using the terminal's mouse, keyboard, and display, combining the effects of remote login and the shared network file system. The 9P protocol, all programs that wish to provide services as files to other programs speak a unified protocol called 9P. Compared to other systems, this reduces the number of custom programming interfaces. 9P is a generic medium agnostic byte-oriented protocol that provides for messages delivered between a server and a client. The protocol is used to refer to and communicate with the processes, programs, and the data, including both the user interface and the network. With the release of the 4th edition, it was modified and renamed to 9P 2000. Unlike most other operating systems, Plan9 does not provide the special application programming interfaces such as Berkeley sockets or X resources or IOCTL system calls. to access devices. Instead, Plan9 device drivers implement their control interface as a file system so that the hardware can be accessed by the ordinary file input-output operations, read and write. Consequently, sharing the device across the network can be accomplished by mounting the corresponding directory tree to the target machine. Union directories and namespaces. Plan9 allows the user to collect the files called names from different directory trees in a single location. The resulting union directory behaves as the concatenation of the underlying directories. The order of the concatenation can be controlled. If the constituent directories contain files having the same name, a listing of the union directory ls or lc will simply report duplicate names. Resolution of a single path name is performed top to down. If the directories top and bottom are unioned into U with top first, then U/name denotes top/name if it exists, bottom/name only if it exists, and top/name does not exist, and no file if neither exists. No recursive unioning of subdirectories is performed, so if top/subdirectory exists, the files in bottom/subdirectory are not accessible through the union. A union directory can be created by using the bind command. There is an example with 3 lines in the show notes, which reads, the first command is bind /arm/bin space/bin, then bind -a/acme/bin/arm space/bin, and the third one is bind -b/user/alice/bin space/bin. In this example, in the first command, arm/bin is mounted as bin, as you probably have guessed. The contents of /arm/bin replacing the previous contents of /bin. Acme's bin directory is then union mounted after bin with the second command, bin bind -a/acme/bin/arm space/bin. And in the third command, Alice's personal bin directory is union mounted before with a /b. So bind, that's the third command, bind -b/user/alice/bin space/bin. When a file is requested from this union/bin, it is first looked for in /user/alice/bin, then in /arm/bin, and then finally in acme /acme/bin/arm. Because with the -b that goes at the front of the line, the -a goes the end of the line, and the one without any dashes and letters, the first command, that becomes in the middle. The separate process namespaces thus replace the notion of a search path in the shell, where Unix shells have a list of directories to search for programs when given a command. The Plan9 shell only looks in the directory /bin. Adding commands is done by binding several directories together to appear as a single /bin. Furthermore, the kernel can keep separate mount tables for each process, and can thus provide each process with its own file system namespace. Processes namespaces can be constructed independently, and the user may work simultaneously with programs that have heterogeneous namespaces. Namespaces may be used to create an isolated environment similar to chroot, but in a more secure way. Plan9's Union directory architecture inspired 4.4 BSD and Linux Union file system implementations, although the developers of the BSD Union mounting facility found that the non-recursive merging of directories in Plan9 is too restrictive for general purpose use. Special virtual file systems, the /proc, instead of having system calls specifically for process management, Plan9 provides the /proc file system. Each process appears as a directory containing information and control files which can be manipulated by the ordinary file system I/O system calls. The file system approach allows Plan9 processes to be managed with simple file management tools such as ls and cat. However, the processes cannot be copied and moved as files. /net Plan9 does not have specialized system calls or IOCTLs for accessing the networking stack or networking hardware. Instead, the /net file system is used. Network connections are controlled by reading and writing control messages to control files. Subdirectories such as /net/TCP and /net/UDP are used as an interface to their respective protocols. Software for Plan9. As a benefit from the system's design, most tasks in Plan9 can be accomplished by using ls, cat, grep, cp and aram utilities in combination with the rc shell, which is the default Plan9 shell. Factotum is an authentication and key management server for Plan9. It handles authentication on behalf of other programs, such as that both secret keys and implementation details need only be known to Factotum. Graphical programs. Unlike Unix, Plan9 was designed with graphics in mind. After booting, a Plan9 terminal will run the windowing system, in which the user can create new windows displaying RC. Graphical programs invoked from this shell replace it in its window. The Plumber provides an inter-process communication mechanism which allows system-wide hyperlinking. SAM and ECME are Plan9's text editors. Storage system. Plan9 supports the KFS, PAQ, CWFS, FAT and fossil file systems. The last was designed at Bell Labs specifically for Plan9 and provides snapshot storage capability. It can be used directly with a hard drive or backed with Venti, an archival file system and permanent data storage system. The software development. The distribution package for Plan9 includes special compiler variants and programming languages and provides a tailored set of libraries along with a windowing user interface system specific to Plan9. The bulk of the system is written in a dialect of C, NCC with some extensions and some other features left out. The compilers for this language were custom built with portability in mind. According to their author, they compile quickly, load slowly, and produce medium quality object code. A concurrent programming language called Aleph was available in the first two editions, but was then dropped for maintenance reasons and replaced by a threading library for C. Regarding Unix compatibility, through Plan9 was supposed to be further development of Unix concepts. Compatibility with the pre-existing Unix software was never the goal for the project. Many command line utilities of Plan9 share the names of Unix counterparts but work differently. Plan9 can support POSIX applications and can emulate the Berkeley socket interface through the ANSI POSIX environment that implements an interface close to ANSI C and POSIX with some common extensions. The native Plan9 C interfaces conform to NIDA standard. It also includes a POSIX compatible shell. The ANSI POSIX environment's authors claim to have used it to port the X Windows system to Plan9, although they do not ship X11 because supporting it properly is too big of a job. Some Linux binaries can be used with the help of Linux EMU, a Linux emulator application. However, it is still a work in progress. Vice versa, the VX32 virtual machine allows a slightly modified Plan9 kernel to run as a user process in Linux, supporting unmodified Plan9 programs. Let me see how much material I have left, because I only have 4 minutes left and it's not gonna be enough. So I think that talking about the Acme text editor, and after about Inferno, and maybe I have to add some more to it. That will be episode 3, which is gonna be episode 78, and that will conclude again this 3-part episode covering Oberon, Plan9 and Inferno. I might include in the last episode, in episode 78, after Acme and Inferno, I might include one of these other inspired operating systems by Plan9, which I mentioned in my show note. Maybe I will pick one of them up and talk about them. I think it was Harvey OS was one of them. Let me quickly. Yes, Harvey OS and Jehan OS. Or I can talk a little bit about the forks, so to say, of Plan9, like 9 Front and 9 Legacy, together with one of the inspired operating systems like Harvey OS or Jehan OS, and like that make it into a full episode, because maybe just the Acme part, the Acme text editor and Inferno, what's left, is not enough material, so I will have to add some extra bits and pieces for you. Thank you very much for listening again. One more Saturday of listening to me, which seems to be the thing to go around lately, or since a year and a half. I think I've started this podcast. Yeah, around a year and a half. Not more successful than when I started. I absolutely don't feel any advancement, but knowing that some of you might listen to it and might even enjoy, might even like it. I know black cats definitely like this show. I don't know about the humans, but some cats definitely enjoy it. So thank you very much for listening again, and I would say reach out if you want to, but so far those efforts were not really successful. You people seem pretty shy to reach out, or you maybe never get to the end of these episodes. So whichever way it is, thank you very much for listening, and see you next Saturday.